Hello there. So welcome to our Wednesday lecture for Chapter 6, Energy and Equilibrium. We had talked on Monday about the changes in energy during a chemical reaction with bonds breaking and new chemical bonds forming, and how we could show those energy changes by looking at an energy diagram which showed that collision point, or transition point rather, and how we put all that energy in and gave out all the energy, and we had therefore exothermic reactions if more energy was being given out, and endothermic reactions if more energy was being consumed by the chemicals. So let's move on and talk about collision theory today, and then we'll stop there and leave the introduction to equilibrium chemistry to Friday. As long as we make a start in equilibrium chemistry, then we've made good progress for the second week of the semester, second week of the chapter, I beg your pardon, which will be all about equilibrium chemistry. As I mentioned in the announcements this morning, at this point we'll just go numerically in order for the remaining laboratories. So having already done 7 and 8, next week will be experiment 9, then 10, 11, 12, 13. Okay. So when we get chemicals to react, we need those chemicals to collide with each other. If we get chemical collisions, then we have a chance of breaking the existing chemical bonds. Without that, there'll be no reaction. But just because the chemicals collide doesn't mean that we're going to get reaction. We know that they have to collide with sufficient force to break the existing bonds, but they've also got to break the bonds that we're targeting. Sometimes it isn't an all or nothing job. Sometimes with a reaction with something like chloromethane, it's just one particular bond that we're looking to break. In this case, the carbon to chlorine bond, so that the chlorine falls off and we can form a new bond between the iodine and the carbon to make iodomethane in the chemical's place. Basically a replacement reaction, replacing one thing with another. And it's a like for like replacement, as we talked about in chapter 5, a non-metal switching with another non-metal, specifically another halogen. And so the point of collision also has to be accurate. You've got to be hitting the correct point and the correct part of the molecule. Now, when we think about factors which affect how fast or slow a reaction is, there are 3 basic principles which we can look at in different ways. First one is just the sheer number of collisions, or what we call the frequency of collisions. Oh, someone's waiting on the sidelines. Come in, Bruno. The sheer number of collisions. And if there's more collisions, it just becomes statistically more likely that the bonds are going to break. So a little bit like analogy would be maybe trying to get 10 people to jump over a barrier, and maybe you get 6 or 7 of the people to manage to jump over. But if you just literally throw more people at the problem, or more chemical at the problem, so we get 100 people to try and jump over the barrier instead of just 10, there'll still be people who fail, but we'll collectively get a greater number of people who are jumping over the barrier. Throw a greater amount of chemical at the problem, and we get a greater amount of chemical colliding with enough energy to break the existing bonds. We get more product produced. So sometimes just throwing more stuff at the problem, a greater frequency of collisions, can produce a greater amount of product. We can also try and manipulate the size of that energy barrier, the size of that jump in front of us, by lowering the energy of activation. It's like instead of having everybody jumping over a 4-foot barrier, try and get everybody to jump over a 3-foot barrier instead. And so you should get more people jumping over the barrier. You should get more collisions to be successful or effective if the amount of energy required to break the bonds is diminished. And we can also think about how quickly the molecules are moving, the speed or kinetic energy of the molecules. Molecules which are moving faster collide with more force. And it's a little bit like letting people take a run before they try and jump over the wall instead of just walking up to the wall and trying to jump over it. If they've got more momentum, they're more likely to overcome that barrier. It's the same with molecules. Give them more momentum, they're more likely to overcome that bond breaking barrier. So those are the three principles which are normally at work if we try and speed up or slow down a reaction. We don't always want the reaction to be increased or sped up, because that might cause the reaction to go bad, like if you're trying to make wine, or it could cause something dangerous like an explosion to happen. So sometimes you're trying to slow that reaction down. We've got 5 principal methods for manipulating and changing the speed of the reaction, which we'll look at now. First one is that we can sometimes take advantage of the nature of the reagents. And principally for us, the main idea that we have come across is when we've got ionic compounds added to water. We said a majority of ionic compounds are actually water soluble. And we touched on this briefly in chapter 3. When we say that they are water soluble, it means that they dissociate into individual ions. This is where my pen might be useful. So those chemical bonds between metal and non-metal, strontium and fluorine, those bonds are severed. Those bonds are broken. And so when we add another chemical to the reaction mix, if the bonds are already broken, it reduces the bond breaking energy, that energy of activation, to virtually zero. And we saw this in experiment 7 a couple of weeks ago when we tried it. You had a couple of reactions where you just mixed some solutions together in a test tube, and that almost instantly produced, and sometimes did instantly produce, a solid precipitate. That's because at this point, every single collision that happens causes the formation of a new chemical bond, because all the old bonds are already broken. So instant success when the energy of activation is lowered. And so the main thing to keep in mind is that we haven't changed the number of collisions themselves. They're still colliding the same number of times, but now virtually all of the collisions are effective, successful collisions, because our energy of activation has been decreased and sometimes obliterated down to zero. Also keep in mind that we haven't changed the kinetic energy of the molecules. They're not moving any faster, they're not moving any slower. But when they do collide, because our energy of activation decrease, it's an instant effective collision. So that's our first one. And it's specifically directed towards ionic compounds being added into water to start a chemical reaction. We know that ionic compounds are soluble, and we know how to recognize ionic compounds, which is how would we instantly know a compound is ionic rather than covalent?
With that, between the zero. I mean, like if it's greater than that 1.9.
Well, that's when we're comparing electronegativities. But what is it specifically about the chemical
Having a
compounds?
charge.
Certainly they tend to have charge, although you can't physically see the charge. What is it about the elements which are used? Anyone else? Oh dear. Fundamentals of ion chemistry. We said right at the start we're talking about chemical bonds specifically between a metal and a non-metal. Do If you've got a covalent compound, you don't have metals. Covalent compounds are about bonds between non-metals and metalloids. There are no metals. So it's easy to spot when the compound is ionic because there's a metal present. Looking at our second factor, changes in concentration, just the sheer amount of stuff in the reaction. Of course, when things are less congested, like a picture on the left here, the molecules can move around with limited numbers of chemical collisions, like walking down the corridor during a class time and there's not many people striding around in the corridor. But if we increase the concentration, we increase the congestion in the reaction. And so if you're walking down the corridor during sort of break time between, I don't know, 50 minutes past the hour to 59 minutes past the hour, there's probably a lot of people in the corridor, and that congestion means that there's more likelihood of collisions.
Wow.
You increase the concentration, you increase the number of collisions. And so that will increase the rate of the reaction. Again, it doesn't mean that every single collision is immediately effective, but statistically, if you've got more chemical colliding, there should be more effective collisions. It's like throwing one dart at a dartboard, trying to hit the bullseye, and having 100 darts in your hand and trying to hit the dartboard.
That sounds
You're more
impossible.
likely to you're more likely to be successful the more stuff you can throw at the problem all at once. So increase in the concentration always leads to an increase in the number of collisions and therefore an increase in the rate of the reaction. So collisions increase. The energy of activation itself is unchanged, as is the kinetic energy of the molecules. Let's take a very brief break. My daughter is calling for something. I suspect her hands are just all cheesy from all those cheesy puffs. It's what normally happens. So one sec. So apparently her show had finished on Netflix and it switched over to Octonauts, which was not approved of. Octonauts is for baby's dad, apparently, was the comment, with a mouthful of cheese puffs. Right, so that's the second one, concentration. It's increasing the number of collisions, which therefore increases the rate of reaction. Of course, conversely, if you decrease the concentration, which you could most effectively do by just adding water to dilute the solution that you're using, that would decrease the rate of the reaction as the concentration decreases. Now, a third one, excuse me, third one is looking at catalysts. A catalyst increases the rate of a reaction without being chemically changed itself. Catalysts are unchanged, and it's because the catalyst is just a host, like the host of a really excellent party. Okay, they're just providing the venue, and they might not get very heavily involved themselves. It's everybody else who has to wreck the place and pee in the swimming pool or whatever. So, what a strange example to come up with, but never mind. Anyway, so the catalyst is unaffected by the reaction, and being the host means that it provides a surface for the reaction to occur. So most normally, another chemical comes in onto the surface of the catalyst, and it briefly becomes chemically bonded to the surface. And then the other chemical that it's reacting with, was swinging around, comes in and smashes on that stationary target. It's a lot easier to break the bonds if the target is stationary, and it's a lot easier to hit the correct part of the molecule if the initial molecule has been orientated in a particular way to expose the vulnerable part. And so this makes it easier for effective collisions. It lowers the energy of activation. catalyst lowers the energy of activation, so more of the collisions are effective. But we didn't change the energy of the chemicals, and we didn't change the concentration of the chemicals. Now, in biology, you're probably aware of the analogies which are used for enzymes. One of the chemicals here in blue actually fits onto the surface of the catalyst like a hand in a glove, so it's held in place. The other chemical comes in, it can crack that stationary target, break the bonds, and when that new bond is forged, the chemical that's produced, in this case combining the red and blue molecules, no longer fits on the surface of the catalyst, and so it gently just drifts off, freeing up the surface of the catalyst for more collisions with more reactants. So you only ever need a very small amount of the catalyst to begin with, because it's renewed after every effective collision. So we think about those energy changes, lowering the energy of activation, it does it for both exothermic and endothermic reactions. Notice that the beginning starting energy and the final energy are not changed. So that difference between the energy of the reactants and products stays the same. And so the enthalpy, the heat of the reaction, also stays the same. It's not changed by adding a catalyst. Now, there are lots of enzymes in our body which do this job of catalysis. Whoops. The only one I want to bring to your attention as an example is lactase. Lactase is the enzyme that breaks down complex sugars like lactose, breaks them down in this case into galactose and glucose, the two G sugars. Again, it's about that lactose fitting neatly onto the surface of the catalyst. Then water comes in this hydrolysis reaction, literally breaks the molecule in two, and neither one of the two molecules, products, fits on the surface of the catalyst completely. So lactose is the chemical being broken down by the enzyme lactase into glucose and galactose. Now, some people can't create the enzyme lactase in their body, and so they're not able to break lactose down. And so we say that these people are lactose intolerant. Consequences for that are often things like abdominal bloating, cramps, and sometimes, in severe cases, even diarrhea. So the catalyst doesn't change the concentration, therefore doesn't change the number of collisions. It doesn't change the kinetic energy of the molecules. It's lowering the energy of activation. Okay, any questions so far? We're doing okay? Okay. I'm really glad nobody heard that. Anyway, before moving on, let's mention a new magic word of the week, and that is Tyrannosaurus Rex, in honor of my son, who is crazy about T-Rexes. Okay, moving on to temperature effects. Effective temperature is actually twofold. That temperature increases the kinetic energy of the molecules, and molecules with more kinetic energy are moving faster. So when the molecules collide, if they're moving faster, they collide with more energy. So more of the collisions will have that energy of activation. But there's a second effect. Because the molecules are moving faster, they're colliding much more frequently. So we see an increase in the number of collisions with an increase in temperature. So more of the collisions have the energy and there's more collisions. But keep in mind that we're not saying that the energy of activation has changed. Okay, the energy of activation is unchanged. Just because molecules are moving faster doesn't mean that barrier to an effective collision is any less. Again, it's like that analogy of a standing jump to get over a barrier compared to a running jump. Just because you're running at the barrier, you've got more kinetic energy, doesn't mean that the height of the barrier has changed. So an increase in collisions, an increase in the kinetic energy, but no change in the energy barrier, the energy of activation itself. Of course, conversely, if we decrease temperature, molecules are moving more slowly, we'll see less collisions. Fewer of the collisions will have the energy of activation, and so the reaction would slow down. As a general trend or measure, we normally see that the rate of the reaction doubles for every 10 degrees rise in temperature. So if we had a reaction at room temperature, 20 degrees, which took an hour, and we increased the temperature to 30 degrees, that would double the rate of the reaction. So the reaction would take half the time, just half an hour. If we increase the temperature again to 40 degrees, then we double the rate of the reaction again. And so half the time of the reaction, it would only take 15 minutes. Conversely, from 20 degrees, if we lowered the temperature to 10 degrees, the reaction would be just half the speed, and so it would take twice as long. So the reaction would take 2 hours. Again, that doesn't fit for every reaction, but it's a good general guideline if you're trying to work out how long to give the reaction. Next one we want to look at, I think our final one, is surface area. You take a chemical, one of your initial reactants, and you have it in a big block, then it's only the chemical at the surface which is undergoing collisions. But if you take that chemical and crush or grind it up into a fine powder, although you have the same total volume of chemical, you've got a much greater surface to volume ratio. More of the chemical is exposed to the surface and therefore exposed to chemical collisions. So that causes an increase in collisions and an increase in the rate of the reaction. Again, no change to the energy of activation, no change to the kinetic energy. We only change the kinetic energy normally by changing temperature. So a faster reaction when our starting reagents are ground up into a powder. I don't know if they still do it, but you used to see years ago commercials for painkillers, and some manufacturers like Ascot and others would talk about their drug working faster because it was a ground up powder rather than taking these big capsules to consume. Okay. Another thing to keep in mind when we think about the speed of a reaction, at the very beginning of the reaction, that's when we have our highest concentration. And that's when the rate of the reaction is going to be its fastest. But as the reaction progresses, the reaction becomes a victim of its own success. It uses up those materials, and as it uses up the materials, the concentration decreases. As we've seen, as concentration decreases, the number of collisions decrease. And so the rate of reaction slows. And so if you have a reaction which takes, say, an hour to be complete, you've probably produced 90% of your product in just the first 15 minutes. When you finally stop the reaction, you're producing the least amount of product at this point. Everybody still hear me okay?
Yeah.
In my headphones, I've got all manner of beeps and boops, beeps going on for some reason. I have no idea what my computer is trying to tell me. Sometimes it's about My headphones switching off, but not today, thankfully. Okay, so let's finish with some practice questions. Let's move all this stuff off my desk. Okay, looking at two competing reactions marked as A and B. Label each as exothermic or endothermic. Which reaction would you assume would be faster? Then explain using collision theory what would happen if the temperature in reaction B was lowered, and anything else. And then finally, what would happen if the concentration of chemicals in reaction A were increased? Use collision theory to work out your answer. So we'll take a break, a 5-minute break. I mean, I think we'll probably finish a little bit early today because I don't want to go on to equilibrium chemistry until Friday. See, try and get this all on the screen. But if you're getting a drink of water or So the first one, labeling the reactions as exothermic or endothermic. Looking at the energy diagrams. Remember, the exothermic reactions are the ones which give out more energy than they put in. The endothermic ones are the ones which consume more energy than they put in. Rather than they put out, I beg your pardon. So if we look at the first one, A, the energy going in to reaction A looks like that, but the energy coming back out is only that. So that's what's coming back out is a new bond form, and that's the energy which is going in. In comparison, for the reaction B, there's the energy going in, and just overlap my graphs a little bit. There's all the energy coming out. So clearly, for reaction A, there's more energy going in. And so for reaction A, it's an example of a endothermic reaction. More energy goes in than comes out. Therefore, reaction B is a exothermic reaction. Which reaction is faster? Because the main barrier to the chemical reaction is overcoming that energy of activation, breaking the existing bonds. And so reaction B clearly has a smaller energy of activation. You'll get effective collisions with less energy compared to reaction A, which needs more energy for any of its collisions to be effective. So the faster reaction should be reaction B. I don't know why I went over that. That's probably an easier B. Explain using collision theory what happens if the temperature of reaction B is lowered. So we said with a drop in temperature, it's equivalent to a drop in kinetic energy. We said the effect, in terms of collision theory, was a twofold effect. We'll see a decrease in the number of collisions, but also see a decrease in collisions which have the energy of activation. Decrease in collisions with the energy of activation. Again, that is not saying that we've changed the energy of activation. Now these collisions, instead of getting over the barrier, they're all coming up short and coming up against the barrier wall itself and sliding back down to the start position. So reaction rate slows because of the decreased number of collisions and the decrease in collisions which have the energy of activation. Finally, what would happen if the concentration of chemicals in A is increased? And we've quite simply said an increase in concentration, making things more congested, gives us an increase in collisions. And so we'll get a faster rate of reaction. Always remember when doing these kinds of problems, you're not explaining collision theory if you don't explain what's happening to the number of collisions. Okay, it's not enough to say the reaction's faster or slower. Talk about why it's faster or slower. Are there more collisions? Do more of the collisions have the energy of activation? Do the collisions need less energy because the energy of activation has been lowered? Think about all these different kinds of factors. Okay, let's see, clear that. Let's see. Oh good, I did start the recording again. Sometimes I forget. Right, so on Friday, we'll start talking about equilibrium reactions, which are reversible reactions. We have normally been thinking about our chemistry as a one-way street. Reactants written on the left, turning into the products written on the right. But sometimes the products, as they build in concentration, and therefore increase in the number of collisions, sometimes the products have enough energy as they move around to break their bonds and turn back into the original reactants. So look at that, there's a huge big fat mistake in my notes there. Let's see. I need to correct this and then repost them for the end of the week. I guess that's the simplest thing I can do. So that second equation, we shouldn't have the arrowhead at that end. The arrowhead to show this two-way street should be the other end. There we go. So those products, nitrogen dioxide, can break their bonds and turn back into the dinitrogen tetroxide. So reactants turning into products, but the products also turning into the original reactants. And so we normally show this reversible nature with two arrows, each pointing in the other opposite direction. It's a two-way street. And that sets up a very particular kind of chemistry, especially when it comes to changing temperature or pressure or adding or removing chemicals and how it affects the rates of the reactions. But we'll talk about that on Friday. Any questions before we disappear for lunch? Doing okay? All right, remember chapter 5, homework finishes tonight. Exam will be in the learning lab this afternoon for chapter 5. People can take that up until Friday afternoon when they close. And then we'll have the online test that people can take at 9 o'clock on Friday and also 9 o'clock on Sunday. Okay, guys, have a good day. Wear that mask, stay safe, wash your hands.